All right. Hello, everyone. We are now live on YouTube. I'm very glad to see you. And I'm also very glad that today I see more of you. Some of you didn't switch on videos yesterday, but I see you today. So we will start in 2 minutes. Yesterday it worked really smoothly. I hope it will continue to work smoothly today. And also today we lifted the mandatory muting, so every one of you can unmute himself or herself anytime you wish. Use this option with good taste during the talks to ask questions in time. If this will not work, we will switch to organize question asking. I'm really glad you all joined from all over the world. So I see that participants are still joining. Joseph, are you here?
Yes, I am.
Oh, great. So then we can start in time in a minute. Sasha, are you ready?
Yes. Am I unmuted? Yes.
Yes, you are unmuted. Everything is fine. We can see your sharing.
Yes.
Your Blackboard.
Yellow board.
Very good.
My yellow board.
Your yellow board, yeah. All right, so I'm glad to open the second day of the Zoom conference. Our first speaker for today is Alexander Yom Din from the Hebrew University of Jerusalem. He will tell us about Paley-Wiener theorem for spherical p-adic spaces and Bernstein morphisms.
Okay, thank you, Dima. So first of all, I would like to say that I'm very honored by the invitation to talk at Bernstein's conference. Bernstein's tightly related themes of second adjointness and Bernstein morphisms generated a lot of research lately. So we saw an example in Denise's talk yesterday. And the subject of the current talk will be, in a more modest way, also inspired by trying to gain a better personal understanding of Bernstein morphisms. So I will start by recalling the Paley-Wiener type theorem of Bernstein and Heyermann, which we will want in some sense to generalize. So we start with a connected reductive group over a local non-Archimedean field F. And we consider the following standard action map. I will tell now the notation. So here MG will be the category of smooth G modules. Inside it, we have the full subcategory of objects of finite lengths. And we have the forgetful functor to vector spaces. So we will work over complex numbers in this talk. And we will also, choose Haar measures, disregard difference between functions and distributions. So this map is a standard one, sending D to the endomorphism. So we need for every representation to specify a linear endomorphism. We do it by acting by D, like this. And then the theorem, Bernstein and Heyermann, says that, well, first of all, I is injective. This might be seen as a prior fact. And the main point is to characterize the image of I. So an endomorphism sits in the image of I, if and only if. So we have a first condition, which is less important for us, is that T is fixed by some open compact subgroup. Open compact subgroup in G on both sides. And the second condition, the important one, is that given a parabolic P in G and E an irreducible cuspidal representation of the levy of this parabolic, then given chi an unramified character of this parabolic, of its levy, we can consider the representation V chi being the parabolic induction of E tensor with chi. Then it is standard how to realize all these V chi's on a single space. Let us call it V on single space V.
Excuse me?
Yes.
Do you mind keeping as much as possible on the screen, so right at the very bottom, so that we can see as much as possible what you wrote?
You mean like this? Okay. Thank you. So we realize all V chi on a single space V, basically space of functions on a maximal compact subgroup. And then if we take V in V and alpha in the smooth dual of V, which will also not depend on chi, we can consider, so the following: to each chi we can associate alpha evaluated at T applied to V in the chi's representation. And this should be, so the condition to be in the image is that all such things should be algebraic, which means, well, the space of unramified characters is a complex torus, and this should be algebraic or regular function on this complex torus. So this is the theorem. And now let me reformulate it to basically the same thing, but if this was, so to speak, in representation theoretic terms, I will reformulate in function analytic terms. So we consider curly A of G to be the space of functions on G, which is span of smooth matrix coefficients of smooth representations of finite longs. And then a corresponding analogous, the counterpart of I is the map iota, which goes from smooth functions with compact support to the abstract dual of curly A. So this sends D to the functional, which sends F to the integration of F against D. Then the theorem can be reformulated as saying again that iota is injective, and that, well, a functional lies in the image of iota if and only if. So again, these two conditions, the first one again to be fixed under open compact subgroup, and second one in the notations of above, we consider the matrix coefficient M chi of G being equal to alpha applied to GV, where G applied to V in the chi representation. And we demand that chi maps to L applied to this M chi should be algebraic again. So this is a restatement of the theorem. And now I want to pass to the generalization we want to formulate. So the generalization is to the relative setting, namely, we consider X to be a homogeneous G space, G mod H some closed subgroup in G. And again, so here, let me denote by by this, the uniformly smooth functions on X, meaning smooth functions which are fixed under some open compact subgroup. So this is the union colimit over open compact subgroups of smooth functions which are fixed under with respect to K. And inside this, we consider the space again curly A of X. So those will be the functions generating G representation of finite longs. The smallest G representation.
Sasha?
Yes.
Could you please scroll less? So right in the bottom of your screen and not in the middle.
Yeah, I forgot. Was already said. Yeah.
Thank you.
Okay, so the space of functions for which the smallest subrepresentation containing them is of finite longs. And again, we have this map iota x from smooth functions with compact support on X to functionals on A, given by sending D to the integral on X of, the functionals that sends F to integration against D. And we again will want to characterize, say, the image of iota.
What do you do here with measures?
I said in this talk I will not care.
Okay.
But you can say, yeah, what to do. So yes, so now what we will want to do will not be for arbitrary X. So we have assumptions. So write them now. So the main assumption is that X is so-called F spherical. F was our ground field. This means that for a minimal parabolic P in G, P has open orbit on X. And second assumption is that X has a finite multiplicity property. And this conjecturally always holds when the first assumption holds. So in some families of cases, it's known by results of, for example, the Lorm and Sakelaridis-Venkatesh. But this property says that given high a smooth character of H and V representation of finite longs of G, if you consider the high twisted H coinvariance of V, it should be finite dimensional. These are always finite dimensional. This is the property. We will assume both these properties. And now let me, so maybe like how to morally situate this. So let me maybe say, so the idea of the previous theorem was that we can, at least I think about it like this, that we kind of put in some sense algebraic coordinate charts on curly A of G. And then in order for a functional to be representable by smooth function with compact support, it needs to be algebraic when restricted to these charts. Now there is a work of the Lorm, Haring, Sakelaridis for some spherical spaces X, which gives Paley-Wiener theorems. So I think at least morally one can think that using Bernstein morphisms along boundary degenerations, they produce again this coordinates, so to speak, algebraic coordinates charts on curly A of X. And the idea of what we will try to do now is that you would like to be ignorant about these Bernstein morphisms, and then how would you proceed? So one possibility is maybe
Sasha, excuse me.
Yeah.
Could you please repeat condition 2? It was too fast. I didn't catch it. So it's you explaining what finite multiplicity property is, right?
Yes, that for any smooth character of H and any representation of G of finite longs, the H coinvariants of V high twisted are finite dimensional.
Okay. And could you please also repeat about charts? I didn't catch the idea.
Yeah, so this is kind of motivational. It's not meant to be precise that this M highs, where are they? So M highs, so those are elements of curly A of G parameterized by high in an algebraic variety. So I think of them as kind of some charts covering our curly A of G. So
you have to fix a matrix coefficient like vector and vector, or here something a bit different?
Yeah, whatever we fixed, minimal parabolic, cuspidal, and vector.
No, but you also some vector, yes?
Yeah, vector and covector. Yes, so you get a lot of such charts which somehow in some sense cover and give it an algebraic structure. And then for a functional to be representable, you need it to be algebraic along these charts. And if I understand, I didn't internalize all the details, but I guess in the work of the Lorm, Haring, Sakellarides, for at least some spherical spaces, they also produce such charts using Bernstein morphisms along boundary degenerations. At least when if I understood correctly, when the combinatorial structure of such degenerations is nice. And the idea of what we will now try to do is to somehow ignore this information of Bernstein morphisms, and then how to construct charts. So I will want simply to define what is in some sense algebraic chart and consider all such things. But then we kind of relegate the question to why there are enough in some sense charts, how to know there are any. And I think again, at least morally, the idea will be that the sphericity of X guarantees that somehow the situation of G itself covers well the situation of X. And then kind of by usual ideology of algebraic geometry that say when you have a coherent sheaf, there is a stratification along which it is locally free and so on. You will somehow abstractly deduce that there are enough charts. But this is just how I see it. It's not meant to be formal. So now I will state the theorem we want to state now, unless you have some questions. So the theorem will be again under these two assumptions. So it will again, you have that iota is injective. And so L is in the image of iota if and only if you give a criterion. So first again is that it's fixed under open compact subgroup under the G action. And second is that, well, L is algebraic, but here the way it is transferred to next defining what is algebraic. So this is the theorem. And now we will want to define what is algebraic. So for this, first of all, let us topologize our spaces. So we will deal with linear topological vector spaces, meaning there is a basis of neighborhoods of zero consisting of open subspaces, open linear subspaces. So linear TVS. So we have our space of uniformly smooth functions. It is the colimit of the k-invariant subspaces. So each k-invariant subspace we topologize by declaring functionals of evaluation at a point to be continuous. Evaluating at points of X should be continuous. We topologize in this way, and this we topologize as the colimit in the colimit topology, and curly A of X we topologize with the subspace topology. So here, let me note on the side that if you take the continuous dual of these uniformly smooth functions, so this will be the limit over K of smooth functions with compact support, which are k-invariant. And you can, by restriction, map to functionals on curly A. And this is basically our map iota. With the limit incorporated, that doesn't matter for now. So what we will want to do is to define a subspace of algebraic functionals. Iota will factor through this subspace. And then the theorem will be that this is a bijection. Iota is a bijection. This is a reformulation simply of the theorem. So now let me define what are the algebraic functionals. So I will do it a bit more generally. I don't know if it 100% helps or not, but let us do it. So V will be a linear topological vector space.
Actually, I'm sorry. I'm very slow. So I got confused again. So your iota goes from compactly supported functions or from compactly supported functions? No.
Yes, but better maybe to drop the first condition. Better to just make it go from the limit of compactly supported functions. Overall K with averagings.
But limit to co-limit.
Well,
I mean, are you taking?
Yes. Each function in curly A is fixed under some K.
No, I'm not worried about K. I'm worried about compact support. So iota goes from functions with compact support, no?
Yes, each term here has a compact support.
So it's co-limit. It's union, right? It's limit over K. I'm sorry. Yes, I see. But maybe.
So the map is that if you want to evaluate now on some element in curly A, this element is fixed by some K. So you take the case term, project on the case term in the limit, and then pair.
Yes. Okay.
It's kind of I don't know how to call it, compact things, which if you deal with them, you drop the first annoying condition. Okay, it's just a technicality, I guess. Is it okay? So now V is some linear topological vector space. So we will want to define what are algebraic functionals on V. We have, of course, also.
Sorry, another question. Is there an example of a spherical variety that doesn't have this finite multiplicity condition?
So I said that I think it's conjectured that they always have it.
Okay, great. Thanks.
But it's not known in all cases. So there is, to be honest, some circularity because, for example, in Sakellarides Venkatesh, they prove it in some cases using Bernstein morphisms and so on. But not formal circularity, but in ideology kind of. But anyway, so we will want now to define what are algebraic functionals on LTVSV. So first we define what given Z and affine C variety. So scheme of finite type over C, we define the notion of Z family. So algebraic Z family in V. This will be the following thing. So we first, sorry, I always go to the top. We have what I will call PDZ. It stands for punctual distributions, not this Poisson divide. The other thing. So PD is punctual distributions. It will be functionals, the space of functionals on OZ, which can be factored via finite dimensional quotient algebra. And then a Z family will be a linear map phi from PDZ to V, a linear map, satisfying two properties. So first is that in the abstract setting, you would say that the image of phi is prelinearly compact. The definition of that is that it has a basis of neighborhoods of zero consisting of open linear subspaces which have finite codimension. So it's some sense dense in a linearly compact thing. But let me immediately say that when V is our example of curly A of X, then this will amount simply to saying that the image lies in some K invariance for some K. And the second condition is that for every continuous functional on V, if you compose phi with L, so this will be a functional on p-dz, you require it to be algebraic. Well, what does it mean? So tautologically in p-dz, in the functionals on p-dz sits the ring of regular functions because by definition p-dz is paired with OZ. And the functional is called algebraic if it sits in this subspace. So it's kind of, so to speak, governed by an algebraic function. So this is the second condition, and here it's enough to check for L, which are evaluations at points of X. You need that the evaluation at each point is algebraic in this sense. Okay, so this is some formalization. What is a algebraic Z parameter is algebraic family in V, which for us will be curly A of X. And then you say that the functional L on V is algebraic if for every such Z family. So this means for every Z and for every phi. If you compose L with phi, again, you get an algebraic functional on p-dz. This is definition of algebraic functional.
Sasha, could you please give an example if V was finite dimensional? So presumably,
yes.
Algebraic family means just tensor product V tensor OZ, right?
Right, exactly. It will be an element of OZ tensor V.
And what does it mean, algebraic functional? Everything is algebraic.
Well, yes, everything. Right.
Mm-hmm. And in general, you can express algebraic families as some kind of completed tensor product, right? It's just a way to reformulate it.
Yeah, I think so, that you start with the notion for finite dimensional and then for limits of such, you mean something like this, yes?
Yes.
Yes, but yeah.
But so it's very strange. It's some kind of intrinsic notion. I mean, can you express algebraic? So your V is, it's some kind of pro-finite dimensional or something. Can't you say explicitly what algebraic means? It's a property of a topological vector space, and it's
yes. That's why I formulated it here like this, to express that I can extract an abstract property which I don't know any use of, but for a LTVS you have this property.
But it seems very
example.
strange that you have to appeal to algebraic varieties to express this property. Presumably, you can express it just in terms of without appealing to algebraic geometry at all.
Okay, maybe you're right.
Yeah.
We will need to think about it. Yeah.
Thank you.
Yes, I agree. There is something something to digest regarding this property, but
so in our case, the space is just a ascending union of finite dimensional spaces, and the topology comes from this.
Not really.
Or it's not finite dimensional
of linearly compact ones. So so our uniformly smooth thing is a union of those things which are simply functions on a discrete set.
But they're not compactly supported, yes?
Yes, but they have this compact topology, so to speak, of you require evaluations at points to be continuous.
And this condition of algebraicity, so if the function are just coming from some, okay, I don't really have a question, sorry.
Okay, so Yes, I agree. I present it in some packaged way, but maybe one should unpackage again and think more. Okay, and then you can extract this property. Let's say, for example, that V sits in W. It has this Paley-Wiener property. If you, when you restrict continuous functionals on W to algebraic functionals on V, this is a bijection. So this actually means just two things, simply that V is dense in W and algebraic functionals on V are automatically continuous. And then you can restate the theorem as saying that the inclusion of curly A in uniformly smooth functions has this Paley-Wiener property. Okay, this is the end of this first part, and now I will move to how to prove this property. So for the proof, we go back again to representation theoretic formulation. So again, I will start a bit from far. So let M be some C-linear abelian category, let's say closed under colimits, small colimits. So you have again the full subcategory of objects of finite lengths, and we will consider two functors D and C from functors from M to vector spaces. And here I put L, which stands for functors commuting with colimits. And then you have this restriction map to try. So home from D to C, you can map to home from D to C when restricted to objects of finite length. And now I will want to define a subspace of algebraic morphisms such that this arrow will naturally factor, obviously will factor. And then you would like to formulate some condition under which to guarantee that this is a bijection. Oh, it did something crazy, yes. That this arrow, left arrow is a bijection. So this will be kind of a categorical Paley-Wiener type statement of this algebraic Paley-Wiener flavor. So let me first then define what is the algebraic function morphism. So T a morphism from D to C on objects of finite lengths is algebraic. Now I define. So again, we fix some data. So Z is again a fine C variety. And M, we would like to be a Z family of objects of finite lengths. So formally what it means that is M sits in M. Z family means that you have a map, algebra map from OZ to the endomorphisms of M. And finite lengths means that for every W in Z, a zero-dimensional closed subscheme, when you restrict M to W, which formally means tensoring with OW over OZ, this will be of finite lengths. So you have such a family, and now you take D in D, and alpha OZ linear map from C of M to OZ. So OZ linear, OZ model map. And now, of course, you imagine that if T would lift to actual morphism from D to C, then you could take our D, map it under T to C of M, and then under alpha map to O of Z, and obtain an element of O of Z. So now we will want to formulate this element without having this map. So the requirement is as follows, that there exists A in OZ, such that, again, for any W in Z, zero-dimensional, closed subscheme, you could do the following. You take our A and restrict it to OW, obtaining some element, or you could take our D in D of M restricted to W. Then since M restricted to W has finite longs, you can map under T. C of M restricted is the same as C of M restricted, and then map via alpha. So in this way, you obtain another element, and you require that they're the same. So basically, A kind of governs this potential element under all restrictions to zero-dimensional subsets.
Sasha, could you please repeat what the quantifiers are? Yes, you're giving the definition of algebraic natural transformations. So
yes,
natural transformations, algebraic. So what are the quantifiers?
Like this, that for every z m with this OZ module map, OZ, thing, D and alpha, vector and covector, so to speak, you have a condition. The condition is the existence of A in OZ, which governs, which wants to be this element here, if T was defined on M.
Yes, thank you.
So under all restrictions to this finite long things, it will be this element. This is the condition. So this is the definition of an algebraic morphism. And now we have a proposition. I will not state precisely, but under some conditions on the category M and on the functor C, for any D was the one we mapped from, so home from D to C, restricted to home from D to C on finite long thing, okay, to the subspace of things which are algebraic, is a bijection. And the conditions have the flavor of, basically existence of enough compact projective objects with some finiteness properties, which will make them nice Z families over the center, and some finiteness property of C applied to such objects. I will not write now precisely. And I guess the idea is somehow that when confronted with a nice family, you will want to figure out who is T applied to D. It should be some element in C of M. Then this condition will give you who should be its images under all morphisms to O of Z. But this leaves out kind of things supported on smaller dimensional subvarieties of Z. And then you need some inductive procedure. Yes, so maybe I don't have the words now to formalize.
But Sasha, so in this theorem, so must be some key property that tells you that, I mean, there is enough commutative algebras by which you can test, right? Because
so somehow
it's the center, right? Is the key word.
Objects whose endomorphism algebra is finitely generated over its center and things like this.
I see. So the center is the key word. Like if there was no center, you wouldn't. So the large center basically guarantees what.
Large center, which of course I will tell now a bit later. In our case, you have by Bernstein's theory of, the center and so on.
Thank you.
Yeah. So maybe maybe pedagogically, maybe I should have right here the conditions. But anyway, okay. And also as a remark and a note, which somehow I used later. I don't know if it's really necessary, but I guess it's might be useful that when you come to check, say under these conditions, suppose they are satisfied, and you want to check that a homomorphism T, a morphism T is algebraic, then you don't actually need to check on all Z. So you can show that it is algebraic if so the following thing. So it is algebraic when your family is parameterized by A1, and it is generically algebraic. I will tell now for Z being a bigger affine space, or any affine space. And generically, algebraic basically means that here in the definition, you require the existence of A only on a dense open subset of Z. It's easy to formulate precisely. So kind of generically on Z, you have this A, which governs your morphism. So this is some criterion. That you can have. Okay, so now maybe I will tell how this abstract thing is related to the previous setup, how to prove the theorem using this. So in our setup, M will be, again, MG, smooth models over G. D will be the forgetful functor to vector spaces, and C will be the functor of taking coinvariance with respect to H. And the relation is the following commutative diagram. So we have morphisms from forgetful to coinvariance. We have them restricted to finite length objects. And so now we claim we have the following dictionary. So this will be isomorphic to our space we encountered before of the continuous dual of the uniformly smooth functions on X. Recall X is a G mod H. And the lower thing will be isomorphic to the space of abstract functionals on curly A of X. And this will be basically our iota again. Here it's the restriction. So this is so basically what is a morphism from forgetful to coinvariance? It's for every V a linear map from V to its H coinvariance. So for the upper thing, you would need to plug in the Hecke algebra smooth functions with compact support on G, and you will get a map to the H coinvariance, which is functions on G mod H. And then if you take as an idempotent EK, it will map to some element here. So this will be exactly an element. This will define you an element in this limit. So anyway, I hinted here it's easy to construct the relation from right to left upstairs. And downstairs, well, downstairs by the finite multiplicity property, a map like this for V being of finite lengths is the same as a bilinear pairing of V with the H invariant functionals on V. And then basically you take, if you want from the right thing to construct a functional on curly A, you take an element in curly A, you would like to produce a number. So you pair it via this pairing with the functional of evaluation at the origin, and you obtain a number. Anyway, some relatively straightforward procedures like this give you this commutative diagram. And then roughly speaking, you check that algebraic here will correspond to algebraic here. And well, and then our theorem that iota is bijective will be this claim that this restriction is bijective. And so this will be some claims that the conditions of the proposition above, which I didn't state precisely, hold in our case. So like we said, it will be basically using the compact projective objects one obtains using Bernstein's theory of the center, second adjointness, and so on, plus a fact of Eisenbud-Gurevich-Sayag. So this kind of will be the finiteness conditions for the category, and for the functor C, you have this fact which uses the sphericity that if you take smooth functions with compact support on X, take some K invariance, some open compact K, then as a model for the Hecke algebra, this will be finitely generated. this is the finiteness for the functor of coinvariance. So you just simply plug in these results to verify the conditions of the proposition hold. So this basically finishes, I think, this section. Unless you have questions, I will go now to the section trying to describe how to construct Bernstein morphisms in this approach.
Where did you use the assumption that G mod H is spherical?
So I guess I'll also say in smaller details, like in this thing, we have to use the finite multiplicity property to translate such a morphism to such a pairing. So this requires the finite multiplicity. And in this statement of Eisenburg-Gurevich-Sayag, you use that X is spherical. Okay, so now I will try to describe Bernstein morphisms. So basically, again, so we have our G mod H, and we would like, in some sense, degenerate it into some degenerated G mod H0, some other closed subgroup H0. And corresponding to that, we would like to produce so-called Bernstein map from smooth functions with compact support here to here. So they were defined by Bezrukavnikov in a particular case, and in a much greater generality by Sakelaridis Venkatesh. And okay, let us see now how it goes in this setting. So you would like to somehow describe the data of degeneracy, this degeneration. I will not try now to relate it to the standard, treatments when you have spherical roots and so on. I will do just the kind of bare minimum to speak about things. So the bare minimum is that we choose some gamma in G, which kind of its powers will degenerate our H. So I will describe now the axioms I found, kind of minimal axioms you would like for it is that gamma is, well, gamma sits in some split torus in G, let's say. And second is that for any open compact subgroup K, exists an open neighborhood of the identity in G, such that for large N, you have the following. So G gamma to the N EK. So this is something in the Hecke algebra. And you compare it to gamma to the N EK, and those should be equal upon projecting to the H coinvariance with respect to the left action of H on G. So you have this condition, which I cannot now verbally say why it is the condition, but let me then proceed. Okay, so maybe one of the simplest examples will be to take G to be SL2, H to be the fixed points of transpose inverse, and gamma to be this diagonal element where pi is a uniformizer. And now, what is H0? So I found to define it like this. When I say I found it, it is in the sense that don't trust this to be the most correct thing. But for now, so G in H0, I define H0 to consist of G such that, again, for every open compact subgroup K, for large enough N, you have the following property. So somehow here G sits on the right. So this is the definition of H0. You check immediately it's a closed subgroup and so on. And in our example of above, so you immediately check that edge intersected with the diagonal times U minus the lower triangular unipotent matrices sits in H0. And I didn't check formally, but probably this is an equality. So this is kind of the degeneration. And now how to define the Bernstein morphisms. So you start with basically the classical idea of Castleman's canonical pairing, which is kind of Bernstein's stuff for representations of finite longs. So this will give rise to the following functional. So let us call it a simp in curly A of G mod H. It will be a H0 invariant functional. So to define it, a simp of some F, I recall very briefly, you consider the sequence N maps to...
Sasha, I'm sorry, I'm lost as to what you're doing. So you wanted to use the Paley-Wiener theorem to define the Bernstein map, is that correct?
Yes, so now I will kind of do the Bernstein map on finite long things, which is basically Castleman's canonical pairing. And then would like to say that this is algebraic in the above sense, so extends to all models. And so,
right, but so can you say this, it's a map from where to where on finite length things?
In the beginning, I will try to define some G mod H0 and the map like this.
Correct, but now on finite length things, it's supposed to be a map between what and what? It's a map on the A's, right, or something?
Well, so maybe we will now immediately see maybe.
Yeah, okay, thank you.
So I see. Okay, so let me then, if you ask already, let me postpone what is the definition of a simp for a second. So from this invariant functional a simp by Frobenius reciprocity, you will obtain a G invariant map, a simp with big A, from curly A of G mod H to curly A of G mod H0. Then the theorem, in the kind of functional analytic formulation, you can formulate that this bigger simp is continuous with respect to the topologies we gave in the beginning. And then if you take its continuous dual, the dual map on the space of continuous functionals, basically this will be our Bernstein map. Because smooth functions with compact support is the continuous dual of this. Well, it sits in the continuous dual, and for our spherical space, it is equal by this main theorem. So in this formulation, one would like to see that this simp is continuous, and then its continuous dual will be the Bernstein map. Okay. So
thank you. Yes.
Okay. Now let me briefly just remind the spirit of defining the smaller simp. So smaller simp of some F, we would like to get a number. So we consider the sequence N maps to F of gamma to the N. Let us call this sequence say phi. Then we consider on the space of sequences parameterized by natural numbers, the shift operator to the side that erases some data. And then this phi will be finite vector with respect to this shift. So you will be able to decompose it uniquely into sum of two parts where, you know, the shift has only 0 generalized eigenvalues and non-zero. And then a simp F is phi not 0 evaluated at 0. So this is kind of the stabilized value at 0 of F.
How do you know that it will be finite?
Well, basically by the same tricks that I read. You take the K invariant representation and consider the operator, this padded gamma to the N. And of course, you will use somewhere this property. I don't know if I now can verbally say, but so basically it goes in the same way.
finite dimensionality and some properties of this degeneration.
Yes, so the properties are minimally packaged simply in this property.
Mm-hmm.
You know, we display with the Ivahori-Brua factorization. Gamma will be positive with respect to some parabolic. You contract something, expand something.
Mm.
But I don't know how to say it verbally now
Okay,
to be clear. But basically, it's the same stuff like Kasselman's classical thing. Okay, so now maybe let me just then again explain how to show this continuous. Then, you know, again, it was a theatrical trick. So this is in the functional analytic formulation, and now I will want simply to convert to the representation theoretic formulation. So by the commutative diagram we explained above, this functional asimp is has the same information as map B from these functors of coinvariance with respect to H0 to coinvariance with respect to H. So this asimp is the same as by this comparison we showed above. And now the main theorem will be reformulated here, the above theorem, as saying that this B is algebraic in our sense of being algebraic, which by the above theorem will say that it extends to a morphism between functors on the whole categories. And then now finally we need then to explain why it is algebraic. So this I'm not sure if I have the best treatment, but how I was able to do it. So I use this criterion to check on such families. So you need to check on A1 that it's honestly algebraic, and on other affine spaces that it's generically algebraic. So to check that it's generically algebraic is not very hard. Basically, it is algebraic because you can write from linear algebra expression from this via some polynomial which annihilates shift applied to phi. And then the point is that this polynomial has the first non-zero coefficient, which might vanish at some point of your variety Z. So where it doesn't vanish, you will have an algebraic, uniform algebraic expression, and you will show algebraicity. So it's not very hard to show the generic algebraicity. And then the problem is why for A1 families, it is actually algebraic. And then what I did, well, used so Bernstein's stabilization lemma, or maybe theorem, I'm not sure how it's called, let's say lemma, plus some strange, maybe not very strange, some lemma, which explains why for A1 I did it. So the lemma is that if you have the ring of functions, the ring of polynomials in one variable, and you have a module which is finitely generated, and you have a transformation endomorphism which is invertible, then there exists a monic polynomial f with coefficients in A, whose free coefficient is a unit in A, such that F annihilates T. And so, like I said, from this fact, then you get nice algebraic formula everywhere on Z. Being a unit in A means that you kind of don't vanish anywhere on the spectrum of this, which is the affine line. So maybe it's not, maybe this proof specific one is not essential. Maybe one can do it in different ways. I don't know. But that's how I showed B is algebraic. So yes, I will stop here.
Sasha, can I ask you a question? You referred several times to the Castleman's map. I don't know what you're referring to. Can you specify?
I referred precisely kind of to the spirit, how to define this a simp.
But he did. But apparently, Castleman didn't do H. He didn't. He didn't do G.
Defined for a V of finite longs. Yes, he did the version kind of the basic group, the group case. Yes, for V of finite longs, he defined the Jacquet, Jacquet for some parabolic V, tensors de Jacquet of the opposite parabolic of V.
I see.
He defined this pairing, which is like it will correspond to here taking the diagonal in G. And then generating it.
Okay. I'm happy. Yes. Okay. Yes. Thank you.
Yes, I would like to see the beginning of the talk when you rephrase the. Yes, you have the Bernstein Eiermann. Okay, I want to see the Bernstein Eiermann.
Okay.
Because after you rephrase it, and I don't understand, because in the Bernstein Eiermann, there are symmetry condition, intertwining condition. And
you mean the intertwining operators?
Yes.
Well, here it's just packaged in the.
Okay, well, okay. So I understand the Bernstein Eiermann. So I want to see your reformulation of this theorem, which is your starting point.
This reformulation?
Yes. So in this formulation, I don't see any symmetry, intertwining condition. So this is a big change of point of view in the. I don't understand how you can go from this theorem to the theorem of Bernstein-Eiermann and reciprocally. I don't understand this.
Yes, let me see if I can kind of put it into words, but I guess the basic point is this commutative diagram. So this isomorphism, which when you just plug in coinvariance with respect to H to be the forgetful functor, or let me see, I'm not sure. Forgetful functor.
Because I think this is very important to very different way to different theorem in my opinion. Very different theorem.
May I ask you? May I say something here, Patrick? I think this intertwining conditions sit in the algebraicity automatically.
I'm not sure that it's in the algebraicity, because here you have formulation which you can erase the alg. It's simply all abstract functionals on A of X are the same as homomorphisms.
Okay.
But I'm not sure I can now. Maybe I need to think how to put it into words to clarify.
Okay.
But I mean, you just proved this, but maybe.
Okay.
I don't know.
Thank you.
Okay.
Thank you.
May I say a few comments?
Yes.
When you define this finite multiplicity condition, I mean, you did it for every character. I think this works out fine, but I think more correct would be to say that it's a reductive character to factor through the unipotent radical. These are the characters which show up in the Bernstein decomposition. And if you go to the smooth category, then this is an issue. Yeah. So, for instance, if you take H to be n, then you have continuity problems. And then I have another comment or question. I mean, for the group, I mean, you only use principal series in order for this algebraicity. And I wonder to what extent, I mean, this finite multiplicity property, I think, is automatic for principal series, right? because you only have finitely many p orbits on G mod H.
Yes.
And so this seems to be a statement, I mean, this algebraicity on the dependence on principal series, or so maybe you don't need this strong assumption for all.
I see what you say. Maybe it's a good point. I need to trace the proof and see if the finiteness for the principal series suffices. Yes, that's what you mean?
Yes, that's what I meant, yeah.
Okay, yeah, thank you.
I have another question. What
Yes.
do you mean by Bernstein stabilization lemma?
Well, that, you know, so for V, a smooth module, you take the k invariants and you take this ek gamma ek.
We don't see what you're writing.
Need to restart like this. So, well, and some power of this, well, gamma, you know, is some seats and some nice, there's some decomposition, and some power of this will have this stability properties that the space decomposes into its kernel and image, and it's invertible on the image. Is it okay? You want me to write it formally? I mean, Dima?
I got it.
This is like in Bernstein notes, you have stabilization lemma. Oh, I don't know.
Okay, thank you. More questions? Thank you again.
Thank you.
We have a break till 4:15.
Very interesting.
Dima, and what should I do? Dima?
Yes?
So what should I do?
I think you can share your screen.
Okay, at any time, yeah?
Yeah, you're welcome to do that at any time. And I can share your slides if you don't mind. I will share the slides in chat with everyone.
Okay.
But it doesn't replace sharing your screen, of course. It's just
okay. Okay, so I will share it at 4:15. Okay.
I mean, maybe better at 4:10 to see that it works.
Allô?
Okay.
Une seconde. Je débranche, je rebranche, je baisse le son. OK.
Okay, so I'm sharing the slides of Misha Finkelberg.
Okay, thank you. Thank you.
Okay, so see you in 5 minutes, in 10 minutes. I'll try to come back in 5 minutes, just in case.
Thank you.
So, Misha, would you like to start sharing your screen?
Okay, maybe I'll share it in 5 minutes.
Okay, very good.
I mean, otherwise, when I share it, I cannot see anybody at all, which is somewhat disconcerting.
I see.
So I remind people that we will have at the end of the conference a group photo and dinner/lunch, depending on your time.
Very nice.
Миша, привет.
Здравствуйте, Володя.
Здравствуйте. Я сейчас в институте for Advanced Study, и я думаю, что это я вызвал все события, потому что когда я собрался в институт, то, конечно, должна была быть эпидемия, и чтобы институт закрылся первый раз со всей историей.
Да.
Вот.
А вы знаете, Володя, что Эрнест Борисович Вильберг умер от коронавируса?
От коронавируса даже?
Да, да.
Как же он не поберегся все-таки? Да. Вот такие дела, печально.
Миша, когда он умер?
Только что, вот сегодня.
Ой, Господи. Винберг умер. Винберг умер от коронавируса. Вот это да. Математика. Кроме всего прочего, он главный редактор, статью ему послали. Я не знаю, что будет со статьей с нашей. Ее приняли, но второй раз он мне не послал это. Он сегодня умер от коронавируса.
Okay, so our second speaker for today is Michael Finkelberg from Moscow. He will talk about elliptic zastava. Please.
Thank you. It is a very big honor for me to speak at this conference. So I thank the organizers. I remember that when I was a student of Joseph Bernstein some 30 years ago. There were notes by Joseph Bernstein about analytic continuation of Eisenstein series, and miraculously, these notes did not disappear. Quite the opposite. Recently, they have appeared as a joint work of Joseph Bernstein and Erez Lapid. But 30 years ago, I was so much impressed by these notes that I have spent my whole life trying just to learn the definition of Eisenstein series. And I learned that there are certain integrals over the moduli space of G bundles over a curve in the functional case, and G bundles with a flag. So we'll study the case of, or the full flag, that is G bundles with reduction to a Borel subgroup. And we will study a certain version of this called zastava, when in background we have also an extra reduction to the opposite unipotent subgroup. This is called open zastava space, and it is the nice finite dimensional smooth variety connected of dimension twice the degree, that is the sum of components, the coordinates in the basis of positive co-roots. And this variety, open zastava, has many nice features. One of the important features is the factorization projection to the configuration space of the curve. And this projection just remembers where these two structures, B structure and minus structure, are not transversal. So they have to be generically transversal, but along some divisor, they intersect not transversally. And this is the image of our factorization projection. Somehow this zastava space, with respect to this factorization projection, has a local structure. Just roughly speaking, we're in the complex case, it means that for any analytic disk inside our curve, the preimage of factorization projection is independent of the ambient curve. But later on, we'll say it more intelligently. So in a sense, zastava does not depend much on the global curve, but still, to some extent, it does depend, and we'll study this dependence. So the first case, the most...
Misha, excuse me, I didn't have time to read the previous slide. Could you please return and just wait half a minute?
Oh, yes. Okay. So shall we go on? So let's first study the case when our curve is projective line and even smaller, even affine line. So we'll require that our N minus and B structures are transversal at the particular infinite point of projective line. Then we obtain a smooth affine variety with configuration projection to the configuration space of affine line. And this variety is very well known to physicists. So from the physics point of view, this is the moduli space of Euclidean monopoles with the gauge group that is the maximal compact subgroup of our G, with maximal symmetry breaking at infinity. This corresponds to the Borel structure, and of topological charge alpha. So this moduli space can be constructed as some infinite dimensional hypercolor reduction and so it carries a hypercolor structure, and in particular, holomorphic symplectic form. Now, this holomorphic symplectic form can be described purely mathematically in modular terms as follows. So it is known that the classifying stack of the group G has a two-shifted symplectic structure, and the natural map from classifying space of Borel to the classifying space of G has a coisotropic structure. And now our zastava space is in equivalent definition the space of based maps from projective line with marked point at infinity to the flag variety. In other words, just a fiber of the natural projection from moduli space of Borel bundles trivialized at infinity to the moduli space of G bundles trivialized at infinity, namely the fiber over the trivial G bundle. Now, this moduli space of G bundles trivialized at infinity carries a natural one-shifted symplectic structure, and this projection from Borel bundles is again coisotropic, and the embedding from the point, the trivial bundle, is also coisotropic, and hence their Cartesian product, the fiber in question, has the symplectic, well, Poisson, but it appears to be symplectic structure, and such an elegant interpretation is due to Tony Pantev and Theodore Spade. So I will write down an explicit formula for this symplectic structure, but to this end, I will need to introduce some explicit coordinates on the zastava space. And we will need this factorization projection to configuration space of our curve, a fine line in this case. Now the factorization property, this is the correct formulation of locality, means that the fiber of factorization projection of zastava over a divisor, which is disjoint union of smaller divisors of smaller degrees, is just the direct product of fibers of zastava of smaller degrees. Okay, it means that to describe the zastava space away from all diagonals where all the points and configurations are distinct, it suffices to know how the zastava looks like for the smallest possible degree, just one simple coroot. And then this zastava space is just a surface, a very simple surface, the product of the base, our curve, which is a fine line or additive group in this case, and the fiber is a multiplicative group. Okay, so this means that for arbitrary degree away from diagonals, our zastava space is locally just the product of those surfaces. So it has, so to say, horizontal coordinates in the affine line and vertical coordinates in the multiplicative group. But we can permute them in each color. Okay, now we have the explicit coordinates, and here's the explicit formula for a symplectic structure. But I will only write it down for simply laced group G. So I will consider its Dynkin diagram and choose an orientation of edges. And then I will write down some new coordinates, namely I will modify the vertical coordinates. I will multiply them by some products of differences of horizontal coordinates. And then these new coordinates are, so to say, Darboux or logarithmic Darboux. The brackets of horizontal and new vertical coordinates are vertical coordinates. Okay. And then from this formula in particular, it follows that the factorization projection from zastava to configuration space is an integrable system. And this integrable system is also very well known. Say in the simplest case, when G is just SL2 and degree is then just a positive integer. This is the Atiyah-Hitchin system introduced in their book on magnetic monopoles. And in fact, this integrable system is known in quite a few other guises. For example, just for SL2 again, in degree D, it coincides with the open Toda system for GLD. So the base is interpreted as the constant slice for general linear Lie algebra. And the total space is the universal centralizer. So the pairs of element in the Lie algebra slice and commuting invertible matrix. Yet another interpretation. We may consider this surface, which is the zastava for the smallest degree, the product of additive and multiplicative group. It has the Hilbert scheme of degree D, but we only need some open part of this Hilbert scheme, the transversal Hilbert scheme, consisting of those subschemes of D points whose projection to the base, to a fine line, is a closed embedding. Okay, now this surface S is a group, the direct product of two groups. It carries an invariant symplectic form, and so its Hilbert scheme inherits symplectic structure, and this is the symplectic structure which is obtained on the open zastava. Okay, so I have many equivalent descriptions of zastava already for SL2, and we will need one more description coming from physics, from supersymmetric quantum field theory, quiver gauge theory. So the quiver will be our oriented Dynkin graph, and the representation of this quiver will remember the degree of zastava. So for each vertex will have the a-dimensional space there, the coordinate of our degree. The group will be, the gauge group will be the product of the general linear groups at the vertices, and the presentation will be just as usual in the quiver variety business, the direct sum of homomorphisms over edges. Now, given a gauge group and its representation, there is a notion of Coulomb branch. We will not need the exact definition. I will just recall that in the work of Braverman and Nakajima, there was recently given a mathematical rigorous definition as a spectrum of some equivariant Borel-Moore homology of certain variety of triples over the fine Grassmannian of this gauge group. But from the physics point of view, this variety is symplectically dual to the usual Hamiltonian reduction of the cotangent bundle to this quiver variety, quiver representation space with respect to the gauge group. In fact, you might notice that in this case there is no framing, and so the Nakajima quiver variety is just a point, but it's a meaningful point. In particular, it means that the symplectically dual variety of zastava space is smooth. Okay, now this Coulomb branch also has a canonical integrable system that is realized as the embedding of equivariant cohomology of a point into the equivariant homology of this variety of triples. And the spectrum of equivariant cohomology of point is our configuration space on the affine line. And this is the integrable system. We had the factorization integrable system. Okay. So this was about the zastava over affine line. And this affine line is a one-dimensional group, the additive group. And now we'd like to study the other one-dimensional groups. The next case is multiplicative group. In this case, the ambient curve is again the projective line. And we consider the similar zastava. Also, we just additionally require that the n minus and b structures are transversal not only at infinity, but also at 0. So this way we obtain an open piece of additive zastava, the multiplicative zastava. Again, it is very well known in physics. It is the moduli space of periodic monopoles. And again, it can be obtained by infinite dimensional hypercolor reduction. So it carries a hypercolor structure, but this hypercolor structure is much more non-trivial. So in particular, it has the whole sphere worth of complex structures. And in the additive case, these were all isomorphic. But in the multiplicative case, they are not isomorphic, and only one of them corresponds to the multiplicative zastava. And again, it carries some natural symplectic structure, but though the zastava itself is an open piece of the additive one, the symplectic structure is not the restriction of symplectic structure on the additive zastava. Say in the minimal case, when the degree is a simple co-root, the multiplicative zastava is the square of multiplicative group, and the symplectic structure is the product of two, the Poisson bracket of two coordinates is their product. So it's, so to say, the doubly logarithmic. And it, once again, it differs from the restriction of additive structure. So once again, the factorization projection to configurations on multiplicative group is integrable system. It is very well known already in the case of SL2. Now it coincides with the relativistic open to the system for GLD. And so the multiplicative zastava is the universal group centralizer discovered by George Lustig. So now the both commuting elements in the Lie group. And again, for SL2, this zastava is a transversal Hilbert scheme of some surface, and this surface is now the square of multiplicative group. Again, it has some interpretation in terms of Coulomb branch, namely it's a K-theoretic Coulomb branch. And one new feature is that it carries a natural cluster structure. This was not so for additive zastava. Okay, so now we can move to the third one-dimensional group, elliptic curve. So we have seen the additive group, the multiplicative group, and now the elliptic curve. And let's start from the simplest case when G is SL2 again. So the corresponding surface is just the product of the elliptic curve and the multiplicative group. Once again, it is a commutative group, so it carries an invariant symplectic structure. And its transversal Hilbert scheme is an open subvariety in the cotangent bundle of configuration space. Now comes an unpleasant surprise. The open zastava space is an open subvariety of the tangent bundle. So it's not isomorphic to Hilbert scheme anymore, and does not carry any symplectic structure. So unfortunately, the nice picture we had for additive and multiplicative case breaks down, and there is nothing to be done. So thank you for your attention. But since we still have whatever, about an hour before Roman's talk, and there is no coffee break, let me offer some consolatory remarks. So in order to be able to do something, we'll have to study the relative compactification of our open zastava, and then we will somehow modify it to make it more like Hilbert scheme. Now, this compactification arises from embedding into so-called Beilinson-Drinfeld-Grassmannian of our elliptic curve. The point is that when we have transversal and N minus and B structures, they define the trivialization of our G bundle. So since our N minus and B structures are assumed generically to be transversal, we get a generic trivialization of G bundle, and this is exactly a point of Beilinson-Drinfeld-Grassmannian, maybe partly symmetrized. And the compactification I mentioned is just the closure of open zastava in this Beilinson-Drinfeld-Grassmannian. Say in case of SL2, it will be a fiber-wise compactification of the tangent bundle. But in general, this compactification has some modular meaning. Namely, this is the moduli space of G bundles equipped with so-called generalized N minus and B structures. And also, since we're generalizing things, we'll also generalize the notion of N minus structure. We allow some twist of N minus structure. So for SL2, the data we consider are, first of all, the SL2 bundle, that is two-dimensional bundle V with trivialized determinant, then an invertible subsheaf L. So if it is a line subbundle, then it is just a B structure, but we generalize it and allow invertible subsheaves. And the notion of N minus structure is generalized as a morphism from our two-dimensional bundle V to another invertible sheaf K, and it's not necessarily surjective. If it is surjective, it is just another B minus structure. And if it's not, it's generalized B minus structure or twisted N minus structure. But the fact that they are generically transversal means that the composition of embedding of L and projection to K is not zero, and the degree is the length of cokernel of this composition. So we fix this twist K, and what we obtain is the so-called twisted compactified zastava. Now it was for SL2, but for general G, it looks very similar. So we just consider all the possible associated vector bundles associated to irreducible representations of G, and consider the similar data for these vector bundles subject to Pluke relations. Now the twist is a T bundle, and then we induce linear bundles from this. Okay, now this is the definition, but then Ivan Mirkovich discovered a very explicit projective embedding of this compactified zastava, and this projective embedding is due to the determinant line bundle on the Beilinson-Drinfeld-Grassmannian. And the fact that the zastava in this embedding can be very explicitly described is due to the fact discovered by Saint-Van Ju that if we restrict the determinant line bundle to the torus fixed points in zastava, then the global sections remain the same. So the restriction from global sections from zastava to torus fixed points is an isomorphism. And the global sections on the torus fixed points can be very explicitly defined. Namely, the torus fixed points are, well, they have many components, connected components, numbered by decomposition of alpha into sum of two smaller degrees. Somehow these smaller degrees, they number the defects of subbundle and the quotient bundle. And the contribution of such a connected component is sort of Fourier-Mukai transform of symmetric power of our twist. So we have this twisting bundle K. We take the symmetric powers on E beta, then we lift it to the product of two configuration spaces, then we twist it by some line bundle. We don't need the exact formula, just we would only need to know that it's some twist along diagonals, some combination of diagonals, and then push it forward to E alpha. And this is the result. In particular, since we do this with line bundles, we know that the dimension of the resulting vector bundle on E alpha will be just the sum of all these degrees, of all the degrees of Q. And this will be the sum of binomial coefficients. It'll be just 2 to the power of alpha. So we obtain some factorizable vector bundle, V alpha. And again, away from diagonals by factorization, to describe this vector bundle, we only need to know it for the minimal possible degrees, simple co-roots. And in this case, this is just direct sum of trivial line bundle and the twisting line bundle. Okay, and the zastava, compactified zastava itself is just the projectivization of this two-dimensional vector bundle. So it's a projective bundle, just the surface over our elliptic curve. And in particular, if we go to the arbitrary degree alpha, the compactified zastava away from diagonals is embedded into projectivization of this V, factorizable vector bundle, just by Segre, because for minimal degree we just have projective line, and then the power of this projective line embeds into the projectivization of tensor product of two-dimensional vector bundles. Okay, so this is away from diagonals, and then we just take the closure of this Segre embedding image at the diagonals. And this is Mirkovich description of compactified zastava. This is a very explicit projective embedding of compactified zastava. Okay. Now, if you want to get back the open zastava we started with, we just removed two hyperplane sections. Namely, in this factorizable vector bundle V, we had two vector subbundles of codimension 1. One corresponds to taking all decompositions of alpha into smaller degrees, but one extremal case, and another one, again, all the decompositions except for another extremal case. So these are two hyperplanes. We remove them both and obtain the open zastava. Okay. And now we wanted to modify our zastava to obtain the Hilbert scheme for SL2, if you remember. And this modification is so-called Coulomb version. And again, you don't need the exact formula. It is very similar, just the combination of diagonals is different. Okay, the same thing. We have Fourier-Mukai transform. We twist the symmetric power of our K line bundle on the product of two configurations by some diagonal divisor, and we take it push forward to configuration space E alpha, and it is called Coulomb because it has some relation to elliptic Coulomb range. So we consider now this space of triples over a fine Grassmannian of the gauge group, and we take its equivariant elliptic homology. But yes,
I'm sorry, I'm lost.
Yes.
So just the logic. So
yes,
you had this compactified zastava.
Yes.
It had a projective embedding, and you said that if you remove two particular hyperplanes, you get the open zastava. That's
yes.
clear. So now the Hilbert scheme in these terms is what?
It will appear just in a moment.
But you wrote the formula.
To describe it, I need some other version of this factorizable vector bundle. So I just change the diagonal divisor in definition.
Can you remind how you change? So can you back to the previous slide? I want to see what the difference is.
Okay, so here you twist by some diagonals when points of different colors collide. Yeah,
yes.
Along the edges of graph. Now let's go back. Here it is, and you see that it's somehow more elaborate. There is some diagonal divisor of this sort, but also there are some diagonal divisors when colors are the same. But it doesn't matter much. Just we change the combination of diagonals.
Yes. So it's a vector bundle on the base
it's
whose
always,
projectivization. In whose projectivization?
Absolutely. It's always the 2 to the power alpha dimensional vector bundle.
So it's a vector bundle into whose projectivization we had the embedding of the compactified zastava, right?
Yes.
Okay, thank you. Thank you.
And the meaning of this new bundle, modified Mirkovich bundle, is the equivariant elliptic homology of the variety of triples, but not of the whole variety of triples, but just of the very small part, in fact, the smooth part, because this variety of triples lived over the Grassmannian of the gauge group, and this gauge group was product of general linear groups. Each general linear group has in its Grassmannian the minuscule orbits, that's just the finite dimensional Grassmannians. And we take all the possible products of these minuscule orbits for various vertices of our Dynkin diagram, and their pre-images in these configurations, in this space of triples, and take their elliptic homology. And this will be the bundle U. The vector bundle U has such a meaning in terms of equivariant elliptic homology. Okay, so then we just repeat word for word the story with the Mirkovich bundle. So we obtain a factorizable bundle. Away from diagonals, it looks just the same, because all the difference was in some choice over diagonals. So again, we have the Segre embedding of this product of simplest zastava away from diagonals. Then we take their closure over diagonals. And if we remove two similar hyperplane sections, we get the open Coulomb zastava. And this open Coulomb zastava is isomorphic to the spectrum of equivariant elliptic homology of this space of triples. Okay. Now, as Dennis suggested, in type A1 for SL2, this open Coulomb zastava will be isomorphic to the transversal Hilbert scheme. So just what we wanted. Okay, and in fact, its closure also has some meaning. It also lives inside the Bellin-Sondrin Grassmannian of PGL2, and it's just the fusion of minuscule P1 orbits. The zastava space also lives inside the Grassmannian, but it's the fusion of different P1s. Okay, so
can you say which P1s are the which?
Unfortunately, no, but I just can tell you. These are just minuscule orbits, right? In the Grassmannian of PGL2, there is the minuscule orbit P1, right?
Yes.
And then the Bellin-Sondrin Grassmannian is the fusion of these local Grassmannians, and you take the fusion of these minuscule orbits, and you obtain the Coulomb thing.
And the usual and the usual one, the usual
one, it is also P1, but it is not the G of O orbit. It is some intersection of semi-infinite orbits, right? So, so in terms of
got you.
In terms of torus fixed points, this Coulomb P1 passes through -1 and 1, but
correct.
The zastava one passes through 0 and 2, so to say.
And for an arbitrary group, does this thing also sit in the Bellin-Sondrin Grassmannian?
I don't know. Probably not. I have no idea why. I just don't know.
Thank you.
Sorry. Okay. Now, this Coulomb zastava does have a symplectic structure as opposed to the usual zastava. Say if you define it via elliptic Coulomb branch, this Coulomb branch always comes with a deformation, non-commutative deformation, and so it gives you Poisson structure on the commutative version. And also it has a very explicit formula, so to say, because we know how the zastava looks away from diagonals, just as a product of surfaces. Each surface is a line bundle over elliptic curve without zero section, and it carries a symplectic form invariant with respect to dilations, unique up to multiplicative constant. So the Coulomb zastava away from diagonals also carries a symplectic structure which is just direct sum of those. And it extends smoothly without poles and zeros through the diagonals. So the open Coulomb zastava has a symplectic structure. And it also has the action of torus. And this is a Hamiltonian action. So we can perform a Hamiltonian reduction. Or maybe it's better called quasi-Hamiltonian, because we don't have really a moment map to the Lie algebra of our torus, but instead we have the moment map to the product of Picard varieties of our elliptic curve. Namely, this is just the composition of our factorization projection from zastava to the power of elliptic curve, and then the Abel-Jacobi morphism to the Picard. But anyway, locally, this product of Picards looks like Lie algebra of the torus, so it can be viewed as a moment map, and we can perform the usual Hamiltonian reduction. So we specify a fiber of this quasi-moment map, and then quotient out by the torus. And in fact, this thing, the action of torus is not necessarily free. and the composition of projection and Abel-Jacobi is not necessarily smooth. So what we obtain is really a stack, but at least generically it's a smooth and symplectic variety. And again, it is well known to physicists, namely as the moduli space of doubly periodic monopoles. Sergei Cherkes calls it monoballs. Well, somehow there is no theorem about this, but it is certainly expected to be isomorphic to this reduction. But one funny thing is that we didn't do the reduction in the additive and multiplicative cases. We only do it now. And what we obtain is an analog of so-called centered Euclidean monopoles. So from the point of view of Coulomb branch, we need a Coulomb branch with the gauge group, not product of general linear groups, but product of special linear groups. And as Sergei Cherkes explains, for five-dimensional theory for double periodic monopoles, only this physical theory makes sense. The complete Coulomb zastava somehow does not make sense. And one has to study the centered monopoles. Okay, now going back to the usual zastava, they are not symplectic, but somehow we can mimic this procedure for the Coulomb zastava and define the same thing. Again, we take a fiber of the Abel-Jacobi morphism to Picard variety and take its quotient modulo the torus action. And this Hamiltonian or mock Hamiltonian reduction of the usual zastava has again some modular meaning, namely if our T bundle is degree 0 and regular means that when we consider the induced line bundles with respect to roots of G, then they are never trivial. And so there are no extensions between the corresponding line bundles. So the reduced zastava space is just the moduli space of G bundles of fixed type, namely they're just the direct sums of line bundles. And the flag has again the fixed type of associated graded. So we fix both the ambient G bundle and the associated graded bundle with respect to the absolute cartan. And this is our moduli space. And this moduli space does have a symplectic structure for the same reason it used to have in additive case, namely the moduli space of G and T bundles over elliptic curve. They have one-shifted symplectic structures, and there is a correspondence between them, namely the moduli space of Borel bundles, and this correspondence has a Lagrangian structure, and if we fix the type of G bundle and T bundle, then this sticky point also has a Lagrangian structure, or maybe quasi-tropic structure, and their Cartesian product is our reduced zastava space, so it acquires a natural Poisson structure which is generically symplectic. Okay, and now comes a miracle that though the zastava and Coulomb zastava were different, the reduced zastava are isomorphic. The only thing you have to do is to change the twisting. So if you want the usual reduced zastava, you can obtain them as the Coulomb reduced zastava if you change the twisting depending on the fiber of moment map. Okay, and this is almost the happy end. The only thing we want to know that this isomorphism is a symplectomorphism. Unfortunately, this we do not know yet. It was only checked for SL2 by Mykola Matvichuk, but somehow I have no doubt it must be true for arbitrary G. That's it. Thank you very much.
Is there a reason you expected this isomorphism between modified and usual after reduction?
Well, well, apart from general optimism, no.
Seems like black magic.
Yes, absolutely. Yes. Yes, it does.
But so there's no physics explanation or anything like this?
The thesis somehow, the non-reducing doesn't make sense.
Pardon me?
Physicist, for some reason, the non-reduced one does not make sense in the first place.
Right. The non-reduced Coulomb zastava does not make sense from the physics point of view. Well, if we believe in this identity, then the usual zastava non-reduced also should not make sense.
Thank you.
Are there any further questions? So, if there are no further questions, then let us thank Misha again.
Okay.
And we continue with Roma's talk at 5:30.
At 15 or 30?
30.
Misha finished earlier, but Roma is scheduled to talk at 5:30.
Okay, then we have half an hour for coffee.
Yeah, unexpectedly.
Dima?
Yes?
I'd like to share the screen, but I guess from the device where I may not be logged under my name. It's my wife's iPad, so let's see.
All right.
So I'm trying to do that there, but screen broadcast. Okay. Is this okay? That works. Okay.
So, Roma, will you be writing on it?
Yes. So I'll not on
Very
this,
good.
but I'll open the app. Yes. Oops. Why not continue? Okay.
Okay. Very good.
Okay.
Okay, so meanwhile, Sasha Yom Din shared both his notes that he wrote during the lecture and the slides he decided not to show. So I will share this with you. That's not for the upcoming lecture, that's for the first lecture of the day.
Oh, so maybe I.
So we will also put this on the website.
Are we starting soon? Can you hear me?
Yes, we can hear you. So I'm glad to present Roma Bezrukavnikov from MIT. He will speak about unipotent characters and l-adic sheaves. Please, Roma.
Thank you very much. And it's a pleasure and honor to speak here. I liked Sasha's Brewerman's talk yesterday, so I want to start in a similar way. So just as in his case, much of my talk will be recording things that I learned from Joseph in graduate school, but I've always been a slow student. So I hope to talk about those things more maybe in 5, 10, 15, or 20 years. And other Joseph's birthday conferences. So today I will be talking about the assignment I got from David Kashdan before becoming a Joseph student, during what became my master's study, when he told me to develop the theory of. So David Kashdan told me to develop the theory of character sheaves for loop groups, and so that's what I will be talking about, and just the first steps in doing that assignment. So yeah, so this is a joint project with David and Yakov, and the goal, so maybe I'll start writing here. So the goal is to develop geometric tools, so geometric understanding, so a way to write characters of p-adic groups by which I mean reductive groups over a local field, non-Archimedean local field. And so for today, I will only focus on unipotent characters. So I'll say unipotent. So for the context, I will first need to recall the finite dimensional story. So where the, yeah, I should say that by geometric here, I mean having to do with l-adic sheaves. And so where just ideally the character value is given by trace of Frobenius acting on a stalk of a sheaf. So so maybe geometric, I should say that coming from Grothendieck sheaf function correspondence. So that's what I mean by geometric. So recall very briefly the finite dimensional story. So the answer for finite Chevalier groups, and this is the theory of character sheaves created by Lustig and then developed by many other people whom I will not mention. So maybe I should just say Lustig's theory of character sheaves. So so let so G be a reductive algebraic group over Q, and G will be the group of its points. So first we want, I want somehow the answer to this problem is much nicer and easier in the GLN case. So so this is maybe I'm starting point 1, but so 1A is when G is exactly GLN. So then to every irreducible representation to raw irreducible representation of this finite group G, there corresponds an irreducible perverse sheaf on the algebraic group, equivariant under the conjugation action. So maybe I'll call it F raw in well, dg of G, or maybe like perverse sheaves on G. So this is a subcategory in equivariant. This is my notation for equivariant derived category of constructible sheaves, l-adic constructible sheaves. So let me not write these words. But the key point is that so that the character of this representation is given by exactly the trace of Frobenius on the stalk of the corresponding l-adic sheaf. So I'll just rewrite it on the next page. Maybe I'll be abbreviating this to saying that chi rho is a trace of Frobenius on F rho. To make this more concrete, let me do the following. So let's take an example. So, or rather, special case. Assume that rho is a summand in functions on the flag variety. In other words, that quasi an equivalent condition is that the space of parallel invariant vectors is non-zero. Then, yeah, first of all, such rho, so such rho are in bijection, right, this way, with irreducible representations of the Hecke algebra, which I write H. So this is just the algebra of bi-invariant functions on B mod G mod B. And it is well known that this is isomorphic to the ring to the group algebra of the wild group. So, well, which is of course nothing but the symmetric group. So let me maybe write. So for this reason, you know, to a representation of the fine Chevalier group that corresponds to a representation of the wild group, let me just write that it like rho bar is the corresponding irreducible representation of double. Then I can tell you what this F rho is. So it's just a summand of the Springer sheaf. So it's I'll just write this Springer sheaf tensor over the group ring with rho. And Springer sheaf, let me just recall for you that it's nothing but the direct image of the constant sheaf under the growth index Springer map. So it's pi lowest star or the constant sheaf. Well, I am working l-adically, so I should write it this way, but again, this is a constant sheaf. And well, if I want it to be perverse, I should shift it by something. And pi is the map from G tilde to G, where this is subvariety G mod B times G, consisting of pairs, I mean, of a Borel subgroup and an element contained in that Borel subgroup. Okay, so yeah, there's this well-known theory which says that the wild group acts on this sheaf. Going back to Springer, and then we can form this tensor product, and this defines my sheaf F raw. So, any questions so far? Okay, so now let's still stick to the finite dimensional groups or finite Chevalier groups, but let's now take a general. So let now G be a general reductive group.
I do have a question.
Yes.
So when you say direct summand, you mean with respect to the decomposition to irreducible representation of Sn of the Weyl group?
Sorry, say it again. So when
you said that F raw is a direct summand of the Springer sheaf.
Yes.
So you said direct summand, you mean like W invariant direct summand, or?
Well, it's as written. It's just as a typic component. So you should think of this F raw. You have like finite group action.
Yeah, it's a typical component of the sheaf as a representation of W.
Yeah, that's basically what this formula says.
This formula.
Okay.
Yes. Okay.
I mean, I'm just writing as a typical component in this final way.
Now, yeah, yes. Now I understand. Yes.
Okay. Any other questions? Okay. So now let G be arbitrary, and some of the things I'll say are known under some assumptions, so maybe connected center, or it doesn't matter for me so much. Well, in this case, the life is harder, so the formulation is more difficult, but still, so again, the theory created by Elliptic says that still there is a bijection. So there is an assignment to raw. So raw is again an irreducible representation of G. So one can construct F raw, which is an irreducible perverse sheaf, which is called a character sheaf. But now, so the character of raw is related to, but is not equal. Well, to the trace of Frobenius of F raw. Sorry. So let me briefly recall the formulation, and then I proceed to the more complicated story. So yes, so the set of irreducible representations is partitioned into some subsets, which I called families. I think that's one of the more or less standard terms. It's also related to the notion of two-sided cell, but let me not go into that. And so for each family, I don't have a good notation for it, so I'll just write family. One meaning Elliptic, so it defines, one defines a small finite group. Well, okay, I'll just write this. It's not a good notation. That's okay. Maybe it's a representation, so I'll just write R.
What letter is this? Oh, we've erased it.
R. I already erased it. So this is a script R. So one defines a small finite group. So for classical groups, it can only be a power of Z2, Z mod 2. The most complicated, I guess, is S5. So gamma, which is a gamma R. so that the family itself, the set, is in bijection with irreducible objects in the category of gamma equivariant sheaves on gamma. So it's a finite group on which gamma acts by conjugations. So this is the same as a set of pairs, gamma psi, where gamma is in gamma and psi is in irreducible representation of the centralizer of gamma in gamma. And then, so again, a remark that also was discovered in some form by Elliptic is that one can identify the Grothendieck group of this small category, maybe tensor the field. So it's identified with functions on what I'll write as com gamma. So this is just a set of commuting, yes, and then gamma invariant. So maybe I should write it here. Okay, com gamma. So by so com gamma, I understand the set of commuting pairs in gamma square, such that gamma 1, gamma 2 is equal to gamma 2, gamma 1. And here, this means in functions invariant under conjugation. So the map sends a class of some sheaf f to the function phi f, which sends gamma 1, gamma 2 to trace of gamma 2 on the stock of our sheaf. Again, it's sheaf on a finite set, so it's just a vector space graded by this set.
Oh, by the way, hello?
Yes?
I think it's not quite true what you said. I think this picture is true in some split case. In a non-split case, it's not exactly.
Yeah, okay. So yes, I said I wanted to add this condition, but then I stopped. Yes, yeah, let's see. Thank you. Yes, and then remark is that so this space, so this has an obvious involution. Well, maybe we'll call it phi. We just swaps the two elements. So gamma 1, gamma 2. You know, if you switch the order, they still commute, and you get, commutes with conjugation action. So, so we get some sort of involution. So we get a square matrix indexed by this set, and so and we already said so the transformation matrix between the bases characters of ρ, where ρ is an R, and this trace of Frobenius on F ρ is the matrix of phi. Okay. And again, so this is again theorem by Elliptic in many cases, and then there are other people extended like
Who is phi?
Velocity sequence and short G, I guess, right?
Who is phi?
Phi is this thing on the previous page. So it's just when we rewrite our space of our T group as functions on commuting pairs, then it acquires an obvious evolution where you just swap the two factors.
Okay. Okay.
But the point is that it's the metrics in this in the second presentation, this is obvious, but in the first presentation, it's some. You can write it down. I just want to do this to save time.
Some characters, yes.
It's there's some explicit formula. So this is non-abelian Fourier transform. Page and George work, and also other places under other names.
Why are you calling it non-abelian Fourier transform?
Yes, maybe I should say so. So if so, you can consider so maybe example when gamma is abelian, then sheaves gamma. So the action is trivial. So it's just representations of gamma times the Pontryagin duo.
So I saw that just the non-abelian Fourier transform is just a map between the change of basis between characters of representations and just functions, conjugate invariant functions. And here it's look like you use
you
this
can use
and
the term. There is no the term is not copyrighted, but
okay.
It is,
but it's not identical to this change of basis.
No, but I'm just telling you why it's called non-abelian Fourier transform, because in this case, so this is a self-dual abelian group. So there is a Fourier transform just acting from functions on it to itself. So there is Fourier transform, and you can check it and each exercise that it agrees with. Because basically I kind of did the Fourier transform in along the second factor, and then I switched the factor, so it's the same as just the Fourier transform. Okay. So now maybe so I just want to make some a couple of remarks about this case. And then pass to the infinite dimensional one. So first of all, just a preview of the effect that was important for our thinking about the generalization is that the character sheaves can be thought of as appropriately defined. So Drinfeld center of the well, what I'll call H finite. So H finite is the finite Hecke category of B times B monodromic sheaves or complexes on G. So like something like, well, one notation mean is this, but this, so if I said in words what this means. And again, so there is in different contexts, I don't want to go into details, but there are different ways to make it into a precise statement, and these different ways were treated by different authors. So there was Bernstein who used some homotopy algebra. There was our paper with Finkelberg and Ostrich, where we worked in D module setting and abelian categories. And then there was after this a paper by George also, who worked in also with abelian categories.
What are monodromic sheaves?
Well, it's you know, it's equivariant sheaves, right? So it's just shifting the quotient. And here it's kind of weaker, so it's locally constant on the orbits. So the best definition is that it's equivariant with respect to universal cover
of the group.
So in other words, there can be there can be some you want to allow some monodromy around the Storer section. Okay.
And can you briefly say how just the correspondence work? You start with something in the Drinfeld center, and then at the end you get a sheaf on G.
There is an obvious functor into this direction, because it's like, you know, G equivariant conjugation equivariant functions on the group act on everything, you know, on any functions in any homogeneous space, and you have an obvious analog for sheaves. And then the hard part is to.
But they act. But you want actually an object.
No, well, I mean, this is monoidal. I mean, you certainly know in some form the corresponding statement for functions. But the important thing that for functions, somehow here the situation with sheaves is better than the situation with functions, because there are unipotent cuspidal representations, and this will be acting by 0 on functions on G mod B. And so if you can like write a map for functions, but the character of unipotent representation will go to 0.
So for functions, it just will be integration, averaging on Byzantine 3? And then you do it in this.
Averaging with respect to U.
And with respect to U.
Yes. And
what about T?
Well, that's exactly the difference between monodromic.
Because it's not actually.
And then so for functions, you average up to U, and then you decompose into different characters of T. Generalized kind of eigenspaces. Okay.
Okay.
Okay, and then one last remark here is that so here for finite Chevalier groups, of course, I mean for any finite group, you can think of like this invariant functions. Well, they map isomorphically to this way to co-invariants. And so this you can think of the center of the group ring. And this is like, well, cocenter, or like COG. So this is center. And this is COG modular commutant. So this is cocenter or zeroth Hochschild homology. So for finite dimensional semi-simple algebras, and in particular for group rings, this is all the same, but this will not be won't hold. And yes, and in the literature you can find a similar statement in this shift theoretic context, but this won't be true for p-adic groups.
Shift theoretic context, you mean that instead of centers you do character sheaf, and instead of cocenter something else?
No. Well, I said that character sheaves are the same as the center of the Hecke algebra, but you can also define cocenter
I see.
and show them they are the same, and some people in the audience can explain better than I. But yeah. Okay, so so let me now pass to like more to our work. So now no, I'll reuse. So sorry, but there's no way around it. So now G will be the group of points over non-Archimedean local field. And so this is, there is this loop group which already appeared in other talks. I'll write G double underline. So this is the loop group. So as Denis explained, it's a grouping scheme. Okay, and so again, I want to start with the case of GLN. So then I want to, so I said in the title that in the first minute that I want to work with unipotent representations. And so here, in this case, unipotent means the same as, so suppose that rho, a representation, in fact, it will not even be important that it's irreducible. Can be any finite length.
Double underline is GLN.
Yes, G underline.
Shouldn't this be double underline?
Yes, a double underline as well. The group of GLN.
No, sorry.
Yeah, it's clear what we're talking about. So it's yes, reversal representation of G. As is usual in as Bernstein taught us, we should be continuing smooth representations, and here I'm considering finite length. Irreducible, but I assume that rho is that the space of Iwahori invariant. So recall that we have G is contained like G of 4, and then there's Iwahori subgroup, which is pre-image of Borel under the evaluation map. So I assume that this is if it's irreducible, it's non-zero, but otherwise, I should say that rho is generated by rho I. Okay, and so then so recall that so in G we have this set of compact elements. So it means that the quick way to say it is it's a union of compact subgroups. Well, I'm referring to the topology of the local field. But it means really that all eigenvalues are p-adic integers. Okay, and so again, write the theorem, which is not you, and hopefully will be written sometime soon. That if I consider the character of rho and restricted to this open set of compact elements, Then this is the trace of Frobenius on the Springer sheaf tensor over C of W fine. And derived tensor with rho bar. So what's going on here? So first of all, well, W fine is a fine Weyl group, which is, you know, periodic permutations of integers with some center of mass property. And so rho bar is the following. So representations of rho of the type I described, they correspond to representations of H affine, which is functions on with compact support on G mod I. And this is now, it's not isomorphic to the Weyl group, but it's a deformation. So it is degenerate. So there's some degeneration into group ring of W affine. And so rho bar is a degeneration of rho, and so it and in a way I should say that, you know, this is a kind of you can ask which degeneration, and I don't want to spend much time on this, but I just want to say that I'm doing something reasonably robust because of the right hand side here. This only depends on the K group class of rho bar, and so there's not as much choice here.
So rho is itself is irreducible?
Let's say yes, but I mean,
and rho bar?
Rho bar is not necessarily reducible, no.
And you said its class in the Gaussian group is well defined, and this is only what you care about. Yes.
Yes.
Sorry, and so rho is just a representation of the affine Hecke algebra here. So you don't go to more general unipotent representations.
But I'm still from GLN case.
Oh, you're in GLN case, okay.
Otherwise, it's not at all true. And so idea of proof, I will not go into much detail, but it's oh, sorry, maybe before that, I need still to say, so what is Springer sheaf? So Springer here, it's defined in a similar way to the usual Springer sheaf, but the role of Barrel is played by Iwahori. So Springer is somehow, well, I'm also reusing notation pi. Well, so where pi is the map from affine. Well, again, so it will be like G underline tilde to G double underlined, and this is a subwriting flags times G underline, where this is flags is a affine flag variety, which is essentially, well, I'll just write at the level of points and not to introduce new notations. So it's G mod I. Yes. And then on this object, we have an action of W affine, which is was maybe first considered by Lustig and then studied also in Jouet's thesis, affine Springer action. There's also a paper by Kazdan and Lustig from the 80s. Okay.
And formally, in this theorem, the equality takes place on regular semi-simple elements, right?
Yes, yes. I mean, right, this is the easiest way to say it, although one can make sense of the right-hand side as a distribution.
Oh, you can make the sense of the right-hand side as a distribution. So is it straightforward, or is it something? Is it something difficult?
Yeah, I think it is straightforward. I mean, it's well, a categorified distribution is a functor from familiar category to vector spaces, and this you can decategorify it.
And then the statement for distributions is still true.
Yeah, I think so.
Can you give some hint about it? So if you have a sheaf, you can construct out of it a distribution.
Yes. Well, maybe let's discuss this later. But I mean,
okay.
The starting point for this discussion is Yakov's remark in chat. Or you can continue this discussion in chat while I talk. Yeah, idea proof is it's kind of straightforward. So it's by some consideration, it suffices. It reduces to something you can do forever. Eventually, it reduces to this statement for finite Chevalier groups that I just mentioned. So it's enough for every parachoric P to prove the equality well, first after restriction of on P, after restricting to P, and then also after taking push forward to P bar, which is reductive quotient, pro-unipotent radical. And then this is reduces to finite dimensional statements. I mean, there are some interesting details that I'm throwing under the rug, but basically the rough outline is this. Okay, so so now I want to talk about the general case, which is not completely done. G, general. Maybe let's say split. So, well, let me. So I want to explain a conjecture. Well, with a roadmap for proving it's maybe theorem under construction, but it's not completely worked out. But so let me. So I want to explain a conjunction. Before doing that, I need to introduce some notations. So we already introduced this notation. So if H is a reductive group over I mean, in definition, we will not really use the reductivity, but we will apply it for reductive groups. Is a reductive group over C, say. So we considered this already for finite groups. So this is the variety of commuting pairs. And I mean, those of us who like derived schemes should, think about it, may want to think about it as a derived scheme, but this will not be really important in what is to follow. So I want to consider this
derived scheme because it's not complete intersection.
Yes, so it's a fiber of the one under the commutator map, and it's pretty wild. And so I will. So these are the regular functions, and therein I will consider like some subspaces. So or left. So L. This is L for left, and or right, and or left, right. So this is the following strange condition. So it's a space of functions such that for every, and just give a pointwise condition that for any y, a restriction of f to the centralizer of y times y is locally constant. So it's invariant under. So this is still a group Z of y, and it's invariant under a connected component of the centralizer. And similarly here we have these just the same, but with flipping left and right. It's for any x f restricted to x times the centralizer of x, and left right just the intersection. So this is one kind of preliminary thing, and another I think.
Sorry, I didn't understand. So when you write O, you write functions on the derived scheme or on the classical scheme?
On the usual scheme, yes. It's and I want to say that this locally constants condition includes the condition of lying in zero homology.
Basically, the derived structure is not going to be relevant, or it will be relevant.
No, it won't. Okay.
Can you repeat the definition of OL and O right?
It's just that it's locally constant in either second or first variable, but for each, if I fix the
G is now G double underline.
No, it will be something in the dual group, but I mean, I will say what I mean. It's I'm giving some preliminary definition, so the context is different.
So O is functions, yes?
Yes, regular functions.
So how regular function can be locally constant?
Well, it can. I mean, it doesn't have to, but it can.
So G is like it's like GLN?
For example. Yes.
So locally constant will not just mean constant?
No, but the centralizer can be disconnected. So it's not locally constant altogether. It's locally if I fix.
Okay.
For GLN, it is constant, but for general group, it is not.
Yes.
So for GLN, the intersection O left right is just constant?
Yeah. Okay. Yes, and then I just want to recall some things that I learned in graduate school from Joseph. So now so I want to now I'm going back to the p-adic group. So G is again p-adic group. I mean, it was still. It always was, but just. Okay, so then, so I'll just write maybe, okay, I consider the S of G, so maybe S. so S, it's well, choose the Haar measure. So this is this just locally constant compactly supported functions on G. And then I have the coscenter. Yes, just a moment. Yes, and the invariant distributions are just the dual space to the coscenter, just a linear dual. There is a splitting of the category of representations and also of S. Is the unipotent part, so I'll just write U plus non-U. So this is unipotent. This is non-unipotent. And accordingly, S is just a direct product as U like plus U. And then this is N. And of course, then it follows. So it's just a direct sum of algebras. So the constant also splits.
So you assume that we know what our unipotent representation of p-adic group?
Yes. But so this is some class of representations. I mean, I will later recall the classification, but it's a class of representations. Maybe I'll just say this. That rep of GU contains all irreducible representations such that they are generated by Iwahori vectors. And for GLN, it's an equality, but in general, it's just not an equality. And so there are some, if you know the notion of L packets, then it's the union, irreducible representation, just the union of all L packets containing a thing here. And there L packets, but yes.
So over the stable center is just one block?
Yes. Yes. Okay. So I'll go to the next page. So there is another decomposition which is easy to define. So S. So just first, as I already mentioned, this set of compact elements, and so there's just it's an open-closed subset, so invariant under conjugation. So it can have its complement. And obviously, you can have a decomposition of the space. So it's invariant under conjugation. It's not invariant under convolution. It's not a sum. Unlike the previous thing, it's not a sum of algebras. And then so C of S, since it's coinvariance under the conjugation, it's C of S compact plus C of S non-compact. And so these two decompositions are actually compatible. So it's a lemma. This is not like immediate from the definition, but it's not very hard given known results that S. Sorry, C of S unipotent is also splits. So in other words, we have two decompositions, they're compatible.
I'm sorry, could you remind what is S, what is C?
S is just the Hecke algebra, all functions.
And C is the cosenter.
C is cosenter.
Thank you.
Sorry, it's my wife's iPad, so you get her notifications. Yeah, any other questions? So, okay, yeah, let me state the main conjecture, and maybe I'll have 1 minute to indicate some steps towards it we can make. So it will consist of some parts. So there are canonical isomorphisms. So C unipotent. Yeah, so I will introduce the dual group and the set of, so this is the unipotent set. So it's a direct sum over U in the U module of the conjugation of, or maybe I should say right, of the reductive part of the centralizer. The subgroup, whatever you call it, like reductive. So this is first thing, and the second thing is that.
Sorry, can you read the right hand side? So let's read the O. I mean, you have direct sum over all U.
Sorry, yeah, I misused my notation. So sorry. So I will need to rewrite it actually. So here I need home of that group, and then invariant under conjugation. Using. And now I can write l-adic R. So it's functions on commuting pairs, invariant under conjugation, and also with this funny local constancy condition. And then this, so the subspace is equal to the sum of the same thing, but that will be all left, right. And so okay, and then the next thing that this agrees with, okay, characters and almost characters, and I think maybe I will say this and the time will be over. So recall that unipotent representations, well, irreducible unipotent representations, are in bijection with pairs U S psi, where US is equal to SU and SU are in G check. And psi is a group of components, representations, irreducible representation of pi naught of the centralizer. And yeah, also requirement is that U is semi-simple and U unipotent. And
but as a semi-simple, not U. As a semi-simple.
And then there is a, so we, in fact, there is a irreducible representation, but also a standard representation. And the character, so if rho US rho, it's the same as irreducible if S is compact, and in which case irreducible is temperate. So it's, and the character of rho US rho. So I'm continuing the conjecture. So this is defines a functional from C unipotent to here.
What
and,
is
Hmm?
what is z of su? It's not just the same as z of s times u?
It is the same, yes. So the idea is that this so it sends in terms of the this realization here in part A of the conjecture, it should send a function to evaluation to the corresponding. So first of all, it's a sum over u, so we take fu, and then we restrict it to centralizer of s times s, and then we pair it with psi. But so here's the maybe key point with which I want to end. Is that this space CUC has an obvious involution, because the characterization, I mean, there's commuting variety has an involution. There is this left condition, right condition, but when you impose both, it's
what is CUC?
So it's unipotent and compact. So it's in part B of the conjecture.
Sorry, wait, I think CUC has never appeared before. I think I had some
oh, that's a typo. Sorry, this is a typo.
CUC. So CUC, it's so this is the important part of the cocenter supported on compact elements.
Yes.
Okay.
It's yeah, it was here. Okay. And so the idea is that this involution sends character to almost character, which is a function coming from a character sheaf, for which I don't have time to say what it is. Maybe there's an important remark which I actually should have made much earlier, that so this was originally inspired, and so so this is partly inspired by another Elliptic's paper. So by so George proposed a definition of unipotent character sheaves and generalization, but it's not, at least we don't know if and why this is identical to his proposal, but partly it's, I just want to say that this was basically the starting point on.
Ron, could you say a word how you associate to SU row a character sheaf?
Yes.
Because I think this is what you mean right here.
So I'm maybe I'll say I'm done with the question with the talk, and this will be the last, the first question. So
yes, I think I think that maybe in the answer to that question, can you also explain how your conjecture is related to the theorem you quoted? That probably is related to Dennis's question.
Yeah. I think for GLN, yeah, this basically follows. Okay, so maybe I should, before ending the talk, is that I should say that we can construct a map in. Yeah, maybe it doesn't make sense. So we can make some steps towards it. In particular, we can construct a map in one direction from the unipotent part of the center to this answer, and then make some other steps, but this is the subject of another. Sorry. Okay, so let me stop here.
I think,
can you see my screen? No.
Not anymore, I think.
Okay. Okay, so I'll end the talk, and then I try to share the screen again. So thanks. Okay, thank you. So I don't know. So should I assume that So can you see?
No, we see black screen.
That's so strange. I don't know why. But okay, so I can. Should I try to answer Denis's question?
Please.
But maybe I'll try still to share the screen just again. So. Okay. No. Oh, okay.
Oh.
So. Yes. I mean, this is all based on, you know, categorical games. In particular, one can consider the sort of categorical cocenter. So the cocenter of H, the affine Hecke category, and so this has a coherent realization. So H is this D. Koch G. Chekhov Steinberg by and then this C of H. There's a paper by Bernstein, Nadler, Pregel.
But this is only Wahori, right? This H. I thought you wanted the whole.
Unipotent, yes. I mean, well, as usual, the idea is that, you know, unipotent representations is, as I said, it's kind of the stable piece containing the Iwahori representations. But if you work with categories, then, you know,
okay.
It remembers it.
Okay.
And so this is basically the coherent sheaves on commuting pairs. I mean, there are some things to, so there is single support condition, and also one of the elements in this commuting pair should lie in the neighborhood of unipotent set, but this is roughly the answer. And so I'm just saying that for these parameters, you can define a functor to vept. That you can just the obvious functor that you take the restrict somewhere and take home from psi. The non-obvious part is finiteness conditions, but let's not discuss it now. But then the functor from this cocenter is most by definition conjugation equivariant sheaf. So with this definition, it's so there is another approach to defining what a character sheaf on the loop group is, in particular adopted in George's paper, and similar to what I wrote for GLN. You start with Springer sheaf and tensor it with something. So
yeah, so
comparing these two definitions may be the main step, but which we haven't quite achieved. But we, I think, have some plan of argument at the numerics level, at the level of K group. But yeah, that's.
So may I ask you two more questions? So one is indeed, so I wanted to see the other definition of the character sheaf via the Springer sheaf starting from SU row. That would be question one. Question two, so it's about your conjecture. So it's so given the Nadler-Bernstein-Pregel description of the categorical cocenter, it seems that your so
yeah, that's exactly the approach that we take. And I mean, yes, I said
so the question is, so basically the question is that the trace of the Frobenius on something equals something. That's the conjecture, right?
Say it again.
So I'm saying that given the Nadler-Bernstein equivalence, your conjecture is that taking the trace of the Frobenius commutes with something. That's meaning that meaning that the
well, I mean,
cocenter in the algebra of functions equals the cocenter is the trace of the Frobenius on the categorical cocenter.
Kind of like the bird's eye view is yes.
Say again.
you know, the bird's eye view of this is as you described, but concretely, I don't think that this C unipotent is isomorphic to the trace of Frobenius on this category. I think it injects there, but it's maybe yes, there is an injective map in one direction, but I don't believe it's isomorphic.
I see. But
that said, so yes, maybe I can use this as a pretext to say a couple more words. So yes, so we approach it using this, and then construct this injective map, and in particular, this proving that this pairing with character is some sort of trace formula that, I mean, it's in particular, it involves an alternative way to describe representations, which is pretty much the same as in paper of Krasdan, Lustig, and Ginsburg for representations generated by Hoare vectors. But for other representations, we need to do something else. Although George also classified this representation, but our approach is to use a different construction based on first constructing some categorical representation and then extracting the actual representation from it. Okay, so that's.
Could you say one word? Could you say one word about the Springer sheaf construction for?
Yeah, no, this is very easy. So this is, I mean, it's not very easy, but that's pretty much as was in this 2A. So where I describe things for GLN. So I said that. So as here, you take this. So again, in this approach, we have to separately do the principal series and then induce from cuspidals. So for the principal series, you just take the this. I mean, just literally this. Using this morphism, and in general, you start with some parahoric, take a cuspidal representation. Cuspidal, sorry, character there, and then you proceed this way.
Okay.
So any other questions?
Sorry. Okay, go ahead, Rami.
Okay, I have two questions. So I will ask the first one, and after you the second one. And so I just feel I miss maybe the main part. Can you go back to the slide with a conjecture and maybe just go over it again?
Yes. So the idea is that we want to consider functions on the commuting pairs, right? But and that's where thinking of this trace of Frobenius on the category, on the coscenter category, that's where it leads us. Because
so just the left hand side is CU is just the unipotent part of the coscenter.
Yes. And
the right hand side, so it's abstract isomorphism or it's something concrete?
Well, if you like, it's fully, I mean, it's concrete, and we mean that there is some natural construction using this categorical business. But even without it, if you read the next page, it's characterized uniquely because of density of characters.
Okay, and what is the right hand side?
I'm telling you where, or like what. So if I start with an element in here, if I start with an element in here,
yes,
then I'm telling you, I mean,
so what is the right hand side?
From its image in the right hand side, I'm telling the pairing with every character. So this.
You take unipotent set, and then you take OR of what? What is the commuting variety of O?
No, it's the direct sum over unipotent conjugacy classes. And I think actually maybe I should mention that some decomposition like that, I think, is something that also Joseph taught us in maybe different form in graduate school. There is some story like by Bernstein and Krasdan about core center and its decomposition, and it's
Okay, but just what is written in the right hand side? What are those objects you take?
So for every unipotent conjecture class, and I take commuting pairs of elements in its reductive centralizer. And then I take invariant functions on these commuting pairs, and then I impose this funny condition of local constancy.
Roman G hat is the Langlands dual group.
Yes.
And how it's related to character sheaves?
Well, I'm leading. I mean, the whole point was that to, you know, if you remember the discussion about finite group, and there was this families, and then I rewrote this families like a K group in this.
So when you work in the basis of the right hand side, you get character sheaves.
Right. If I flip, it's roughly the. If I flip the.
Characters are functionals on the left hand side, so you can construct functional on the right hand side, which correspond to what?
Yes, yes. If you like, so this conjecture B implies. So maybe I can write this. So conjecture B. This whole point, it implies that C unipotent compact carries a remarkable involution. Maybe phi, because the two commuting elements anti-symmetrical. And the idea is that phi sends characters of maybe standard representations.
So you really have no statement about characters of irreducible representations, right? You really have no statement about characters of irreducible.
Yes. No, but of course, in many cases, irreducible are standard. But
so characters of standard.
I mean, that should involve some Arthur parameters. That's something that we actually haven't yet.
So it sends character of standard to what? To character sheaves?
Yes. Well, it's almost characters as functions.
But yeah, I see. But it is only on compact, only defined on compact elements.
Yes. For some reason, I don't know if there is a good philosophical explanation for this, but maybe I should mention this thing that so there's this paper of Yakov, like Buttier Kazdan Warszawski. I don't remember how to spell Buttier, but I do remember how to spell Warszawski. Sorry. So they define actually perverse sheaves G like double underline, but so we expect that this character sheaves that appear here, these character sheaves to lie in this perverse.
Good morning.
But so I just want to say that kind of in their approach, it just by definition is supported on some compactly generated set, and character is, you know, so the character of trivial representation can in no way appear from, can in no way correspond to a perverse sheaf in their definition because its support is not compactly generated. So there is something like, at least technical reasons to restrict to compact sets.
Can I ask you a slightly different question? So somehow in the finite dimensional case, the first and sort of easier place where character sheaves appear is not when you study important representations, but when you study arbitrary, for example, generic delinguistic representations, and there's a statement that the character of a delinguistic representation is given by some simple character sheaves. So the question is there some kind of analog of the statement here? And there, the only catch is that if you can start dealing linguistic representation corresponding to a non-split torus, then you have to introduce some kind of non-trivial Veil structure on the character sheaf.
Oh yes, I don't know what. So yes, we have a paper like old work that hopefully again will appear soon. So yes, so with the Yakov, we have similar result. Yeah, thanks for asking. Actually, wanted to mention this for similar result for like generic depth zero L packets, meaning that you take a delinguistic representation on cuspidal delinguistic representation on like reductive quotient of a parahoric, and then you induce and take its L packet of maximal parahoric, and then you induce cuspidal depth zero packets. But I mean, I don't know what
can associate
exactly you have in mind. So one possible, so Charlotte Chen and Alexander Ivanov, they developed some analog of the linguistic theory for high depth representations of p-adic groups. So you know that could also be a possible way to generalize this and connect it there. But you know, we started.
But the story about sort of taking some simple character sheaf and sort of redefining the Veil structure, and does it appear in this business or not?
Say it again. So it takes simple.
Define case somehow. The point is that if you start dealing linguistic representation, then you only need some simple character sheaves, but the only kind of non-trivial thing you need there is to, I mean, if you start dealing with
yeah, this story is very, very much like that, but I don't know, maybe you have
so my question was whether
you can see the line,
procedure, so they also have this procedure.
Maybe I rewrite it, so yeah, for cuspidal depth zero. But I don't know what you're thinking about. I mean, we can discuss it later.
So maybe I more or less want to understand better the same question. So if you're just interested in GLN and in cuspidal representation, but of arbitrary depths, do you have some hope that there will be some character sheaf?
Well, hope yes, but results no.
But you would expect that like something similar should work, or?
I'm an optimistic person, but yeah, I don't think I have anything like. Well, okay, so maybe I should say it this way, that a basis for optimism is that possible basis for optimism could be is that there is this theory of character shifts on unipotent group by Drinfeld and by Yarchenko, and somehow this tail of p-adic group is like unipotent group, so maybe there is a hope, but
can you show some specific point which breaks down, or like
no? Well, okay, so maybe yes, because like one important thing is a fine flag variety is int proper, and the further generalized flag varieties are not.
What generalized?
Well, I mean, you just have to consider G mod I, and if you want high depth, you would have to consider G mod like 10th congruent subgroup, even second congruent subgroup. So this is not
so the geometry of that variety is much more complicated than the variety.
It's again, the technical thing is it's not int proper. It's not like abstract. From some perspective, maybe it's not more complicated, but this compactness, properness is an important technical point. Okay.
Can I ask one more thing?
Okay. Actually, I mean, I'm giving another talk somewhere else in 15 minutes, but
something short, I hope. So in the categorical version of the cocenter, right, there's a functor from that to say sheaves on loop group mod adjoint loop group acting on itself.
Yes.
So did you prove that this is fully faithful?
You mean like functors from?
So from this from this deco on commuting pairs with singular support, like in Bernstein.
Yeah.
And this has a map to sheaves on loop group mod adjoint loop group.
Yeah,
adjoint acting on itself.
I think this is.
I mean, I'm sort of thinking about, okay, maybe.
But maybe we can, yeah. So sorry, actually,
maybe it's the, maybe you can say that for in geometry, the center is always canonical equivalent to the cocenter. Is that's a question?
What do you mean?
No.
So l-adic will vary.
I mean, it's related, but not.
l-adic will vary sheaves at the same, which a priori the center is also the cocenter.
No, not in the loop setting, Dennis. In the loop setting, I don't think it's so. Up to completion.
No. I mean, for large categories, it's true, right? I mean,
for large category, it is true because it's like semi-rigid.
For large categories, yes. I mean, but if it's true for large categories, it's also true for small categories. Compact objects.
No, but like
but the center of
there are different. If you want like this finiteness conditions, like single support and etc., it will be different for center and cocenter. I mean, both are described in terms of coherent sheaves.
No, the center of the big category is like the trace of the big category, but the center of the small.
Okay, so you can take the big center intersected with a small category. That's what you're asking.
No, but in an l-adic setting, there's this problem of tensor product is not sheaves on the product, and then some stuff breaks down. So,
but again, for large categories, it's still true.
Oh yeah, but the question is this center to say that it's fully faithful inside sheaves on this pre-stack.
I think this is true and maybe not very hard, but yeah, maybe we can discuss it further by email.
Yeah.
Okay.
Okay.
Okay, thank you very much.
Thank you. Let's thank speaker again. Okay, and we meet tomorrow at the regular time.
In the same link.